Hey guys, welcome back to another video. In this video, we're going to look at energy graphs of simple harmonic motion, and they're going to be drawn against position. Meaning, on the x-axis, we're going to have the displacement, and on the y-axis, we're going to have the energy plotted, be it the kinetic energy or the potential energy. So we're taking this example of the ball in circular motion, in simple harmonic motion. So we've plotted a few positions. Now, the first graph we're going to look at is kinetic energy against displacement. So first of all, let's fix a key, which is on the left-hand side, on the right-hand side, we're going to take it as negative. On the left-hand side, we're going to take it as positive. Okay, great. Now, for kinetic energy against displacement, the first thing for position 1, it is displaced rightwards of the equilibrium, and it is at the maximum displacement, or called as amplitude or x0. So maximum displacement, and it is in the negative position, meaning it is displaced in the negative direction. Therefore, we're going to plot a point minus a on the x-axis. Why is energy 0? Because at this point, from previous video, you should know velocity is 0. If velocity is 0, in that case, it has no kinetic energy, since half mv squared, v is 0, so the entire value becomes 0. Great. In that case, we know we can plot a point minus a 0 on the graph. Okay. Next point, let's look at position 2. What's happening at position 2? What's happening is the displacement is 0. Therefore, since it is at the equilibrium, we're going to plot a point over here on the y-axis. And what is going to be the y value? The value is going to be maximum anywhere on the y-axis. So let's take up over here where v is maximum. Why is v maximum? You should know that since over here there is no change in height or potential energy is 0, the kinetic energy becomes max. Kinetic energy is max. Because in this position where the displacement is 0, the velocity turns out to be maximum. If you remember from previous video, this is the equation for velocity. Therefore, if indeed displacement is 0, what is the formula? V is plus minus omega x naught, or V is plus minus VA. x0 is amplitude or the maximum displacement. Great. So at the middle position where displacement is 0, in that case, you're going to get the maximum velocity. And when the velocity is maximum, the kinetic energy will indeed be maximum. Okay, so we know the kinetic energy is maximum, so we plot a point highest on the y-axis. Great. Now, coming back to position 3, where the displacement is again maximum, but remember, it is in the positive direction, meaning leftwards, in this direction. Therefore, what's going to happen over here? You're going to plot a point on the positive axis, positive x-axis, called A. Why? Because the displacement is maximum over here. So, it's called x0 or amplitude. Great. So, it's going to be on the x-axis. Why? Because kinetic energy over here again becomes 0. Why 0? Because velocity is indeed 0. Great. Why is velocity 0? If you want to go back to the equation, the equation gives you plus minus omega times root over x0 square minus x square. x0 square meaning amplitude square. And if the displacement is indeed maximum, it is displaced by its amplitude or the maximum displacement. So for the x, you have to plug in x0 and it becomes x0 square. So x0 square minus x0 square. What's it going to give? It's going to give you omega times 0. So velocity becomes 0. Okay, so we know velocity is 0. Great. So again, at position 3, it is lying on the x-axis with a kinetic energy of 0. So for kinetic energy, what you're getting is this curve, which is actually the curve of minus x squared. If you have access to a graphing calculator, or just go online and search the graph for minus x squared, you're going to see that the shape of the curve is actually like this. It is an inverse of, or the opposite of x squared. The opposite of x squared. X squared looks something like this. However, the curve of kinetic energy against displacement is minus x squared. Now, how are we getting this shape of the curve? Obviously, there must be an equation, and you don't need to know the equation and the derivation. However, I'll go through it. Right. So for the equation of kinetic energy, the part on the right side, you know the main equation for kinetic energy, which is half mv squared. Great. So if you know the equation for half mv squared, now what are the variables in this equation? You know half is a constant. You know mass is a constant. The variable is velocity. So let's plug in the equation for velocity. From here, you know the velocity is given by v is equals to plus minus omega times root of a squared minus x squared. So now they want the expression for v squared. So can we figure out the expression for v squared? We can. So we just square either side of the equation. This plus minus becomes plus, and you're going to have omega squared times x naught squared minus x squared. This is what you get. This is what you get for v squared. So let's plug that in. Omega squared times amplitude squared minus displacement squared. Great. So if you get that, let's take out the brackets and take all the constants on one side and all the variables on the other side. These are not all variables, the only variable is this. So we're basically taking apart the maximum kinetic energy, and we're taking apart the variable kinetic energy, which is changing. What I mean by that is, look at over here. What is this giving you? Half m omega squared times x naught squared, which is amplitude squared. So from this, you know, this is giving you maximum kinetic energy. How do I know that? Because in this equation, look at this, omega times x naught is actually the maximum velocity. If you know from over here, right, max velocity is given by a omega, or the amplitude times omega. So if we apply that over here, we know this expression is giving you over here half m times max velocity v max whole squared. So this is actually giving you the maximum kinetic energy. So this part of the equation is giving you maximum possible kinetic energy. And this part is the variable, which is going to change depending on the amplitude, depending on the displacement. Again, what I mean by that is, if you separate the constant part and the variable part, you know that this is not going to change. This is constant. This is applicable for any scenario. If you know the omega square, if you know x naught square, if you know the mass, you can find out the maximum possible energy of the bob, of the bob at any position. This is basically the maximum possible energy of the bob, which is constant throughout. Over here, this, let's say, has an energy of 2 joules. Over here, it's going to have an energy of 2 joules. Over here, it's going to have an energy of 2 joules as well. And you can find that energy, total energy, just by this. If you know the amplitude, if you know omega, you can find out the total energy, which is constant throughout. The kinetic energy may change, the potential energy may change, but the total energy stays constant. All right. So from this, you know this is a constant. You know this is the only variable, because half m omega square is another constant. This is not going to change. The angular speed doesn't change, the mass doesn't change. So what you're getting is minus x square, this and this. So remember, we were just saying that this is a curve of minus x square. This is how we get it. This is why, because of this variable, we are getting a minus x square shaped curve. You don't need to know this, but it's better to understand how it's derived. Right, now you may imagine you must have searched, and the shape that you get is actually something like this. This is the curve for minus x squared, and this is the curve for positive x squared. Now, why is our curve shaped like this? The answer to your question is, remember there is a constant over here and you're subtracting it from this constant. So, in your graphing calculator, plug in, let's say, a random value of 2 minus x squared. You're going to see that the graph or the curve lifts up by 2 values or 2 units. So this is why, since we have a constant in front of minus x squared, our graph looks like this. If you're confused about this, you don't need to understand this. The only thing you need to understand is the kinetic energy graph looks something like this. And the 3 specific plot or coordinates that you need to know is over here, it is minus a, 0. Over here, it is positive a, 0. And over here, it is 0, but Vmax. And what is Vmax? Vmax is, not Vmax, maximum Ke max, or the total energy. So what is the total energy? The total energy is half omega square a square. So that is giving you the total energy, right? This is giving you the total energy, and this is the y coordinate at this point. How is that the total energy? Because this part is a constant. This never changes. So if you plug in x is equals to 0, where the displacement is 0, you're going to see that the value for energy that you get is actually this. So therefore, we know that at any point, the total energy is actually half m omega squared x squared. Right. So at this point, potential energy is 0 and kinetic energy is max. All right, great. So that is how we're getting this maximum kinetic energy, and this is also the value for the total energy, which is constant throughout. Okay, I hope you understand that. Now, I've already talked about how this is giving you the expression for maximum kinetic energy, because when you're getting omega times x naught, that is actually Vmax, maximum velocity. So when you're getting maximum velocity, you're getting maximum kinetic energy. And the only position where you get maximum kinetic energy or maximum velocity is over here. Great. So hopefully you understand how this graph works. Now, if we get back to potential curves, how does it look like? This is basically the right opposite of it. Oh, by the way, kinetic energy or potential energy or energy in general is never negative. So we're never going to take this part. There's not going to be any part of the curve in the negative y-axis. Okay, great. So now for potential energy, how do we plot potential energy curves? Now, let's get back to position 1. Position 1, what is happening is the height is maximum. The displacement, or in the vertical displacement is maximum. And you know, at position 1, velocity is 0. However, you also know that energy is always conserved. Energy is always conserved. And this is the maximum energy, and this is never going to change. This is max kinetic energy, max Ke, and also total energy at any point. So if you know that, you also should understand that at this point, this bob, even though has no kinetic energy, must have potential energy, Pe, which is equal to half m omega square x naught square. So you know, at position 1, the potential energy is maximum. Why? Because the height is maximum. The height that is displaced by is maximum. So, in that case, at position 1, you're getting maximum potential energy. Coming back to position 2, where the displaced height is 0, the total energy remains half m omega squared x squared, but the potential energy is 0. Therefore, we plot a point over here where the energy is 0 and the displacement is 0 as well. The potential energy is 0. Again, coming back to position 3, what's happening over here is the displacement, or the height, is maximum again. Since the change in height is maximum, the potential energy it has is maximum as well. If the potential energy is maximum, you know, it is equal to, again, half m omega squared amplitude squared. So the total energy is this as well, but kinetic energy at this point is 0. So potential energy is maximum and is plotted over here. Now, if you want to know how this curve is, the equation for the curve is derived, it's basically this. This is total energy, let's say, total energy. And you know the total energy again is half m omega squared x naught squared. This never changes. So you can plug that in over here, the total energy. And what is the total energy equal to? Total energy is equal to kinetic energy plus potential energy. What is the equation for kinetic energy? This is the equation for kinetic energy. Oops. Right. This is the equation for kinetic energy. So let's plug that in. Half m omega squared a squared minus half m omega squared x squared. So this is kinetic energy. And what is Pe? That's what we're going to figure it out. That's what we're going to figure out. Potential energy, we don't know. So if we try to simplify the equation and try to make potential energy the subject, what do we get? You know, this and this is the exact same. So you can cancel both out. And what are you left with? Well, there's a negative sign. So take this to the other side. Potential energy is half m omega squared x squared. So now you have an equation for potential energy. This is your equation for potential energy, which is half m omega squared x squared. And this is also why this is the curve you have, where potential energy is proportional to x squared. So if you take your online simulating graph or calculator and you plug in this equation, you're going to see a graph that is synonymous to an x squared graph, right? So this is how we're getting the shape of the curve from the equations. Again, you don't need the equation, but it's good to know. So if we plug both of those equations in the curves here on one plot of x and y axis, we're going to see that the total energy is always, again, constant. This is very important to understand, because when you're going to do the sums, this notion of the total energy remaining the same is going to help you. Great. So if you understand that, this is basically the kinetic energy curve, the red one, and this is basically the potential energy curve, the yellow one. And the sum of both energies at any given point is this orange curve. Right, so that is how you're getting the position graphs, the energy curves against position. Right, so in summary, what are the basic things we need to understand? Total energy stays constant. And what is the expression for total energy? This. That is your expression for total energy. Half m omega square amplitude square. That never changes. And what is the equation for kinetic energy? The maximum energy, or the total energy, minus half m omega square x square. What is the equation for potential energy? It is basically half m omega square x square. With this equation, you will get the value for potential energy at any given point, at any given position. Great. So the Vmax, what is the Vmax? Energy max, Ke max. Again, over here, Ke max. And when is Ke max received? When the velocity is maximum. Okay. So now we understand how the position curves work.